Welcome back. So we'll continue our discussion on this dynamics or the mechanics of this wind turbine. So what we have kind of looked at it, if you recall, uh, uh, we have talked about different kind of loads. Okay, so primary uh, resource or the primary source of those loads are aerodynamics load, which causes your lift and drag. There could be gravity force, inertia force, electromechanical, operational forces which could arise due to brake, yaw, pitch mechanism. Then we talked about types of loads, whether it's steady, cyclic, resonant kind of things, and plastic. So all this, and we took an example to talk about that. So we'll go a little bit details now and try to analyze uh, these loads and all these things on the wind turbine. Okay. So what we do, we start with simple stress and strain definition. Stress and strain. Okay. So we start with that. Now, let's say simple material. Okay. And we kind of bifurcate that. This is the length L. Let's say this is delta L, and there is a force which is acted on it. Okay. And this you consider as a cross-sectional area. Okay. So this is this material is under tension. Now, what uh, we stress, which is sigma force by area. Okay. Obviously, the unit should be in Pascal. Strain, we design the epsilon, which is delta L by L. That means how much length has been increased. And for a material, typical stress strain curve, so if you do, so this goes okay. So this portion is linear, and the slope of this curve, this is gives my essentially this is the slope. This slope is gets me the Young's modulus, which is essentially the slope, and which is a linear curve. So it could be, let's say this is a rise and this is run, then this should be rise over run. This point is yield strength. Somewhere here, this is ultimate tensile strength. Tensile strength. And this point is finally it goes to fracture. Okay. So that's typical um, stress strain card. So for example, let's say, okay, still E is 200 gigapascal, Y is 250 megapascal, and whereas ultimate strength is 500 megapascal. Okay. Now one can find out at which strain does a steel start to deform. At which strain does a steel start to deform plastically or permanently? So what we have, sigma y is A into epsilon y. Okay. And sigma y is essentially y. So my epsilon y is y by E 250 into 200 into 10 to the power 6, 3. So this is 1.25 into 10 to the power 3. Something around 0.125%. So that's you get like that. So similarly, one can say, let's say, you can say, when does a beam start to deform? If you look at the beam structure or if you draw it, let's say I'll this is our center of curvature. This is radius of curvature. This is neutral axis. Okay. This side would be on compression. This is tension or elongation. So this distance is D and this is thickness 2D. So neutral axis to upper surface is D and neutral axis to lower surface is also mm, D. Since the so this point is no space point. Okay. So here simply epsilon y is d by rho, which is your, I mean, that radius of curvature, if you say, okay, rho here. A typical convention that you have in solid mechanics. So you can see the beam situation that one surface would be under tension, the other surface would be on compression, and it depends on this radius of curvature. Now we find out, let static beam bending. Okay, so which is essentially my Euler Bernoulli theory. So what we know from Hooke's law, sigma is E into epsilon. Basically stress, where sigma is stress, E is Young's modulus, epsilon is strain or deformation, whatever you call it. So you can have structure, different kind of structure under different kind of, obviously this is the central axis, then I mean basically these are neutral axis, okay, and these are cross sectional area. You have here you can see the bending, obviously assuming the displacement is orthogonal. So now what we'll do, obviously one can draw a little bit better picture that here the idea is to be important. So this is, let's say, bending radius or radius of curvature. This is neutral axis. This is 2D thickness. This is Z, which is distance A from neutral axis. So this is my side view. This side would be tension, and this is my compression. Okay. Now, if you look at the of the section, this is neutral axis. This is my Z variation. This could be front view. So this is how the so obviously Z here minus D2 plus D. If the neutral axis is 0, then you have this symmetric these things. So this is going from minus D2 plus D. What we can write, strain is epsilon, which is Z by rho, because 1 by rho is D2 Wx by dx2. So what we get, epsilon Z into D2 Wx by dx2. Okay. Now we can find bending moment. So m of x is minus d to d z sigma z d, which one can write z ez d2 wx by dx2 dA. E minus d2d z square dA. This term is nothing but I, which is second moment of area. So what we get, E I d2 wx by dx2. So one can write from here m equals to ei 1 by rho. Okay, that's what the that's what you have as bending moment. Okay, now what we write, the static beam equation or Euler Bernoulli. So d2 by dx2 ex ix dx2 equals to ux. Here You have shear force, which is dmx by dx, which is capital Qx. You have distributed load, that is d2 mx by dx2, which is small qx. So this is what you have, okay, for the static Euler-Bernoulli equation or beam equation. So these are the essentially this is the basic equation. Now we take a simple example. With this, we take a simple example, which is quite often cantilever beam with end load. Probably simplest pattern of loading. So the force is here. And if this is x, this is x equal to L. And this is WL, but here W0 equals to 0, W prime 0 equals to 0. Okay. And that's the length of L. So it's a beam which has been fixed at one end, cantilever beam, which is fixed at one end, and you have an end load acting at the other end of the beam. So what we have, mx equals to ei d2w by dx2, which is f into L minus x. And dm by dx, which is minus f. So dqx by dx is 0 because ei is constant and there is no distributed load. So qx equals to 0. Also, no gravity of the beam. So if we that's what your this is your mx, okay, this is qx, which is that's the variation how it look like. Okay, so what we write now, d2w by dx2 equals to f by ei L minus x from the first equation, which is simple. You get that. So here this is an second order ordinary differential equation. So it can be simply solved. And if you solve, what you get, F by EI, L x square by 2 minus x cube by 6 C naught plus C1x. Now we have initial conditions where W0 is 0, W prime 0 is 0. If I apply that, it gives me C1 equals to 0, C naught equals to 0. So what eventually we get, W by X, if x square by 6 EI EL minus X. So that's a kind of a variation of the displacement along X. That means from here, if you start along the axis at different axial location, one can find out the displacement distance or things like that. So at end point, which is x equal to L, W by L would be FL square 6EI into 2L. This one can write F into L cube by 3EI. One can think about this is displacement, this is force, this is kind of a spin constant. Okay, this is what you get when you have simple cantilever beam with a load at one end, and so the beam is connected at one end fixed and the other end you have loading, and then you get the displacement equation using static Euler Bernoulli. And once you integrate, this is a simple integration here, what you see, and you apply your initial conditions at one end and then find out the equation for displacement at different axial locations along the length or axis of the beam. And final displacement, you can find out how much at the other end the beam is going to be uh, displaced due to the load. Okay, so we'll look at some other example of cantilever beam also and continue this discussion in other session. Thank you.